All right, so as I said, today's lecture is not part of the material for the exam. It's just for your benefit. Also, there will be no homework for it. Maybe that's why there are not too many people. But well, it's a very interesting and modern topic. So specifically, today we're going to apply the formalism of spinor helicity to calculate some things. So the formalism is most useful for gluon amplitudes, and for them, for some particular set of gluon amplitudes, we'll be able to calculate, to write down a complete formula, the Park-Taylor formula. And that formula can be proven using a more general construction for three amplitudes called BCFW construction that we'll describe. All right, so as I said, the formula is more useful for gluon amplitudes. Now, this requires non-abelian gauge theory, so I was a bit hesitant, but it's really the most important application, so it's worth doing here, even though we didn't talk about non-abelian fields. So I'll just start with describing the elements that we need out of non-abelian theory. So the objects are gauge fields called gluons, and the essential difference with respect to electromagnetism is that they are self-interacting. So in electromagnetism, the photons interact only with other fields, but the gluons interact with themselves as well. So in order to do that, however, one needs to have an extra index A. So the gluons are fields with the usual A nu, but also an index A. And then there's a 3-point vertex that involves an object FABC. So this would be called a color index. For historical reasons. And this FABC that appears in the 3-point vertex is the structure constant of some symmetry group, some local symmetry group. Structure constant of a local symmetry group. All right, so this 3-point vertex involves this FABC, but also has to satisfy Lorentz invariance, and since we have, we will have correspondingly 3 indices coming from the gluons, 3 Lorentz indices coming from the gluons, and there's no 3-index invariant, Lorentz invariant. We have to have also derivatives. So the 3-point index, the 3-point vertex is d mu on an A times, well, okay, let's put it already like this. So it's of this type, FABC. So if you want, there's an A nu, A rho, A sigma that is contracted with some delta function and with a momentum. Okay? So the symmetry group has some generators, TA, that are usually considered in the fundamental representation. That means that this TA is a matrix with indices in a fundamental representation I and anti-fundamental representation J bar. So this is then, if this I goes from 1 to n, this is an n by n matrix. Okay. And there are possible normalizations, but one possible normalization is the following. Trace in the adjoint of TA TB is delta AB. So this means that the trace is considered in the adjoint representation. An adjoint representation means that it has the same kind of indices as this, the index A on the generator itself. So this would mean TA BC, CD, TB, DC. This would be trace in the adjoint. But in this case, the normalization in the fundamental representation that is used mostly would be with 1/2. So this is a somewhat standard normalization. So it's one possible canonical normalization. But in the case of spinor helicity, it is often more convenient to consider the trace in the fundamental with 1. So trace fundamental TATB is delta AB. However, you see, in order to go from one to the other, I have to rescale by the generator's TA by a square root of 2. And the structure constant of the symmetry group means one has a relation, commutation relation between the generator where TA commuted with TB. It's proportional to TC with a structure constant FABC. And, well, the existence or not of an I is a convention. And so, however, if we use the spinor helicity convention, where the trace in the fundamental is delta AB, then, as I said, we have to rescale by square root of 2 the generators. And you see, if I multiply with square root of 2 all the generators, then I get an extra square root of 2 in here. Okay? So one can then redefine this whole object, call it F tilde ABC. This I square root 2 F ABC. And then looking here, and if I multiply with another TD, and I take the trace, then on the right hand side I'll have trace TD DC, which is delta CD by the convention. So in here I'll just be left with FABD. So FABD will be equal to trace of this. So F tilde FBD will be equal to trace of TD times the commutator. And then breaking the commutator in two terms, we get that this is equal to trace TA TB TC. Yeah, I can put it on the right. Yeah. Minus trace TC TA TB. Yeah, actually I think perhaps, and here I can use the cyclicity of the trace. No, wait a minute. TA TB TC, TB TA. Then using the cyclicity of the trace, I can put this in the with TA at the beginning. So TA TC TB. Okay, so one can write F tilde ABC in this form. Now, what's the point of this? The point is that, as I said, in the Feynman diagrams, we have 3-point vertices which are proportional to FABC. But FABC, though specifically F tilde ABC, but can be rewritten in terms of these traces. So that means that the amplitudes which contain vertices can be rewritten to contain traces of generators. Okay? So be rewritten to contain trace TA. Now, to be a little bit more general, if I also want to introduce quarks, which are in the fundamental representation, so quarks called QI. I is an index in the fundamental representation. Then the coupling between a QI, an antiquark, QJ, and the gluon is given by, not surprisingly, the thing that has all these three indices, which is TA IJ bar. But remember, these things are thought of as external indices. Right? So if I have a quark, an antiquark, and the gluon, the coupling has this term, which means that more generally, the amplitudes can have traces of generators as well as generators not traced over of this type, corresponding to external states with gluon, quark, and antiquark. So that's a little bit more general. If I don't have quark and antiquark, then I cannot have this object, and then I'm left with just traces. Okay? All right. Yeah, there's one more observation that, in fact, so for the most common gauge group, also relevant for real life or QCD, we would have an SUN gauge group, SUN symmetric group. And in this case, the SUN generators satisfy this relation, completeness relation, ij prime delta I prime j minus 1 over delta I j delta I prime prime. Okay, so in this case, at least we have sums over A's, then we can replace these generators with just deltas, and then we'll just have external lines. Anyway, so this is just to be a little bit more general, to have a notion of how this relates to real physics, the physics of QCD, where you have SUN, SU3 specifically, and we also have quarks. But for the theoretical amplitudes that we'll be studying in this class, we'll restrict ourselves to the ones with just gluons, in which we just have traces. But one more piece of information is that there's one more simplification appearing when you're using the formulation in terms of generators. You find that, so one finds that there is a single ordering of color indices in the amplitude that contributes. This is called color ordered amplitude. So, this color amplitude can be performed at every loop level. However, the formula depends on the loop. So, there's no really simple way of writing a general form. So, since in any case we're interested here with only 3 amplitudes, I'll just write the 3 amplitude formula. So at 3, so this so-called color decomposition at 3 level is so remember that, as I said, we're interested in this lecture in the n-gluon amplitude just with gluons. And then also at 3 level, as I said. So this amplitude that depends on n gluons will be written as, well, since it's 3 level, we know it has to have the coupling to the order g to the other n minus 2. It's usually put outside. And then, as I said, only the color order amplitude is relevant. But to construct a full amplitude, we take the color of the amplitude, multiply with traces, and make permutations. So sum over permutation sigma. So this means permutation modulo cyclic permutations, because so let's say permutations modulo cyclic permutation. Zn is the cyclic group, because the reason of this is the trace itself is cyclic, so permutations inside. So let's be more precise first. So I have a trace of products of generators Ta but the indices are permutations of the indices 1 through n. So Ta sigma 1, Ta sigma 2, until Ta sigma n. So as I said, the trace is cyclic, so the permutations are only defined modulo the cyclic ones. And in here we write this color ordered one, but then inside it we sum over permutations. Okay. So to repeat, that doesn't mean just the color permutation. The color order permutation is the only one that contributes. All of them contribute, but the only one you need to calculate is the color order one. Right?
So why isn't g to the n minus 2?
Well, I mean, let's check it. Simplest case, n equal to 3.
Yeah.
Right. So,
Right, that's it.
and then I just add more. Now there are 4, there are 2, and so on.
Okay. So, right, the interactions is between 3 of them.
Yeah.
That's right. Thank you.
Sure. Okay. So then what does it mean to have color ordering? So this here. Color ordering means only adjacent Mandelstam variables here. So I defined before generalized Mandelstam variables as this. If I have external momenta ki, kj, their square of the sum is called Sij. And then adjacent means like S12, S23, S34, and so on. Right? Only all these things appear. But not, so not S13, etc. These are not adjacent. Okay, so that's what we mean. So, yeah, strictly speaking, I haven't described this, and it's perhaps confusing, but it's worth remembering just as a mnemonic device that when you have amplitudes with gluons, you can describe them. There's something important about this, but you can describe them in terms of double lines. So the gluon is something with a double line. Okay, so then you can think of as colored ordered something where it becomes obvious. Now if I switch these things, suddenly it looks if I reorder, let's say 1 and 2, I put 2 and 1, then this would look twisted, right? So think of this as a natural ordering of this amplitude, and that's the way you should think of as a color order 1. So then that means that this amplitude will depend on this one, S12, on this one, S23, this one, S34, S45, S56, and S61. Right? All right. Okay, so all of these is somewhat confusing information, lots of definitions, but unfortunately they're needed to start describing things, so I'm sorry about the overload. But now that we've defined these things, let's start thinking about what to calculate. So obviously we need to calculate the color ordered amplitude. And so what is the simplest thing we can calculate? Well, the simplest thing would be a 3-point amplitude. It turns out that's actually useful. It's not only simple, it's actually useful. And you might be confused about this because, well, if you've seen anything until now, you've seen that, if you understood things until now, you've seen that we only looked for 4-point amplitudes. I mean, we describe things like this and so on. So why didn't I start with a 3-point amplitude? Well, the reason I didn't start with a 3-point amplitude is because this is kind of singular. Just kinematics, momentum conservation, means that I need to have so let's say I have momenta P1, P2, P3 all in. So P1, P2, P3. Right? Then momentum conservation says that P1 plus P2 equal to minus P3. Right? But what does that mean? Well, you have to remember these are gluons, so P1 squared equal P2 squared equal P3 squared. So let's do this. I square this relation, but P3 squared is 0. That means P1 plus P2 squared is 0. But that means P1 squared plus P2 squared, which are 0, plus 2P1 P2 is equal to 0. So that means that P1 is parallel to P2. And then repeating the argument just by pulling out another one, you see that all of them are parallel. Okay? So P1, P2, P3 are all parallel. Right? So that means that the scattering is only possible, 3-point scattering is only possible if I have either a trivial case, like this, or a somewhat less trivial case, like this. But that also doesn't work, even though it wasn't obvious there. So it's only this case that works. So that looks, kind of very silly, very, I mean, that's not a physical situation, right? So that's why you never talk about the 3-point amplitude. However, we'll see that it's important for this BCFW construction. And to understand a little bit what the problem is and how we could solve it, let's use this spinor helicity formalism. All right. So we've seen that we have this is equal to 0. But moreover, this was equal to S12, right? P1 plus P2 squared. And we've seen last time that in the spinor helicity formalism, S12 was equal to this product. The angle product 1, 2 times the bracket product 2, 1, right? So, and this is 1, 2, and this is 2, 1. So, this product is 0, which means that either this or both are 0, right? So that means that either 1 is proportional to 2 or 1 is proportional to 2. Right? And well, since they're all parallel like this, I can say that in fact either 1 proportional to 2 proportional to 3, or 1 proportional to 2 proportional to 3. But now comes the crucial point. For real momenta, we have seen that 1 is proportional to 1. So the point is, there was a complex conjugate in the proportionality relations. And so if they're real, then they are actually proportional to each other. So that means for real momenta, all of them are 0. All of them are proportional, right? So for real momenta, I have this, and 1 proportional to 2 proportional to 3. All right? However, now if I just invent complex momenta, if I analytically continue, and you saw that this was something that we did already, considering as a way to regularize the poles in the amplitudes. We anyway got a little bit away from the real axis. But now let's consider, just generalizing to arbitrary complex momenta. Then we can have 1 proportional to 2 proportional to 3, but not 1 proportional to 2 proportional to 3. And this would mean that 1, 2 equal to 2, 1 equal to 3 equal to 3, 1 equal to 0, but 1, 2 different 0, and 2, 3 different than 0, 3, 1 different than 0, or the opposite, or these 0 and these non-zero, right? So for complex momenta, I can choose one set of products, let's say the the angle products to be 0 and the bracket products to be non-zero, or the bracket products to be 0 and the angle products to be non-zero. Okay? That's the thing that will help us. All right. So for color ordered amplitudes, we can calculate the gluon 3 vertex. One useful in electromagnetism, and more generally in gauge theory as well, we must choose a gauge. There's a gauge invariance, there's a redundancy in the system, so we must choose a gauge. One useful gauge in this context of the color ordered formalism is the so-called Gervais-Neveu gauge, in which we need to add a gauge fixing term. This is, as I said, I'm sorry that this is information, a lot of information that comes before its natural start, but it's useful. You add such a gauge fixing term, and then the Lagrangian becomes trace minus a half 2ig d mu a nu plus g squared over 2 a nu. Okay, but the relevant thing is that then the vertex in this Gervais-Neveu gauge takes a simple symmetric form. So the 3-point vertex is now minus square root 2 eta mu k1 rho plus eta nu rho k2 mu plus eta rho mu k3 mu. Okay. All right. So, and I should also say that this gauge is not so common in other kinds of calculation that we'll do in QFT2. So this is the only place where you'll see this. It's useful only for, I mean, it probably has some other uses, but I have only seen it in the context of the spinor helicity functions. All right. Just as a warning, so what is the point of this? So we're looking at the color ordered amplitudes, so the cyclicity is part of that. And in this Gervais-Neveu gauge, we have, as you see, there's a trace of the gauge indices. So these things they're all A mu A T A. All of these objects are, when I write A mu, I mean A mu A T A. So the trace acts on the TAs. I have the trace TA T B T C, and then I have a single object of, so that's the point of this Gervais-Neveu gauge, is that I have a single term of the type d mu A. Right? And so I strip the trace, right? And also a square root 2. And once I strip that, I'm left with a momentum times the delta function, or eta. And then by the color ordered notion, I have to add cyclic permutations, and that gives this vertex. Okay? So once I obtain this Lagrangian, the form of the vertex is kind of obvious. All right. Okay, so now let's look for amplitudes of given helicity and the Park-Taylor formula. All right, so let's consider so I was looking at the 3-point amplitude. Let's consider the case where the helicities are like this, minus for 1 and 2 and plus for 3. And then from last time, we have seen that and defined epsilon plus of Ki, which was written in terms, so for gluon, the helicity plus was written in terms of a reference momentum Q. So Ki is the momentum, Q is the reference momentum. And this was given like this. And then in components, in spinor components, this was epsilon plus A dot. This so square root 2 lambda q a lambda I tilde a dot over qi. And then for epsilon minus, this is bracket, well, with a minus bracket, square bracket q gamma mu, sorry, here, yeah, like this. This is the opposite, square root 2 qi. And then this was then minus square root 2 lambda tilde q a dot lambda I a over qi. Okay? So now looking at this, I see what? So if I have, oh, sorry, yeah, I forgot the last point, which is the most important one. So if I then want to calculate the amplitude, I have to contract this vertex with the external helicities, right? So I will do so with epsilon 1 mu, epsilon 2 mu, epsilon 3 rho. I multiply these vertex with the helicities for 1, 2, and 3. And so I get that A3, depending on, well, 1, 2, 3, meaning momenta and helicity for both, is equal to minus root 2, epsilon 1, epsilon 2, epsilon 3, k1, plus epsilon 2, epsilon 3, epsilon 1, k2, plus epsilon 3, epsilon 1, epsilon 2, k3. Okay? So this was the 3-point amplitude depending on momenta and helicities. So now I specialize for this case. The helicities 1 minus, 2 minus, and 3 plus. And I see what? Well, I have this term, epsilon 1 dot epsilon 2, then epsilon 3 dot k1. But this is minus minus, this is plus. And so in epsilon 1 minus epsilon dot epsilon 2 minus, I will have what? So there would be lambda tilde q contracted with lambda tilde q, right? But then I'll have lambda 1 contracted with lambda 2. And then the denominator. So this one would give lambda 1 contracted with lambda 2 means by definition means the angle bracket 1, 2. Right? And then 2, 3. Well, 2, 3. Yeah, the other terms I'm not so sure about. Let's see. So in my notes I have that the other terms are proportional to 2, 3 and with 3, 1. Let's see. Let's see this one first. This would be 3 plus with 1 minus. 3 plus with 1 minus would be lambda 3. So lambda 3 tilde. And with 1 minus would be lambda 1 feel like I'm losing some information in here. Anyway, so I think probably one needs to use some more spinor identities, because there will be a product of brackets, and I probably need to use some spinor identities. But the result would be that the corresponding the other two terms will be proportional to these things. Right? And now comes the issue. Now comes the fact that if the momenta are real, then all of these things are zero. So if momenta are real, I get 0. Okay? The amplitude vanishes. But as I said, it's useful to consider complex momenta. And specifically, from the analysis in here, let me choose actually the opposite convention to what I wrote here. So let me choose the convention where the angled brackets, the square brackets are proportional, and the angled brackets are not. So that 1, 2 is non-zero. All right. So then, after using some algebra and list these spinor identities, one finds that the 3-point amplitude in this case, 1 minus 2 minus 3 plus, is actually I 1, 2 cubed over 2, 3, 3, 1. Okay? So the 3-point amplitude is written only in terms of the non-zero objects, the angle brackets, not the square brackets. So it's non-zero. But then I can do a similar calculation, for instance, and flip the helicities. And then I can write 1 plus, 2 plus, 3 minus as just the complex conjugate of the above, which means minus I. The complex conjugate here gives the other type of bracket. All right. So yeah, in this case, if I chosen this to be non-zero, then this would be 0. But in principle, so these formulas are true for whatever convention I want. Well, moreover, for complex momentum, these are the only possibilities. The only other possibilities would be 1 minus, 2 minus, 2 minus, and 1 plus, 2 plus, 3 plus. But these things are 0. Okay? All right. So, we found a nice simple formula for the 3-point case. But what was the point of this? Well, the point is to go to 4 points and higher. And then, in the case of 4 point and higher, of course, we don't have this kinematical issue. So the amplitude can be non-zero, as you know. But when you consider helicities, the amplitude with some given helicities can be also 0. So these formulae in particular are generalized. So then we will have, let's say, by complex conjugation I can flip the all helicities, so I'll write only one case. So I can have the case with all plus helicities, or even all plus except one, and all of these are actually 0. And so how do I see this? Well, let me not give this proof. You can read it in my notes, because I'm running a little bit late, so I need to choose what I talk about. Anyway, so there's a simple argument that you can look inside the notes having to do with the possibilities of having non-zero objects like this. But then if you have these equal to 0, it means that the first non-zero possibility is to have, say, 2 minuses, or more generally, let me call it, let's say 1 plus, and then an I minus, a J minus, and all the others to be plus. And then this is called maximally helicity violating amplitude. The initials here are MHV, so usually one calls this an MHV amplitude. And the name is a little bit confusing. The point is, in this formula, it's common to use the convention with all momenta going in, which we have been using until now. And in this case, of course, would be all the first possibility is with all the helicities being equal. But now if I go back to the standard convention where some momenta go in and some go out, and we view this as a transition, then when I flip the momentum, I also flip the helicity. So the one with only pluses will want to say that I have only pluses to begin with, but then only minuses coming out. So this would be totally helicity violating, right? I would completely flip helicity. Just that this is 0, and so is the one where I flip everything except 1, which is this one. So the maximally helicity violating is the one where I violate all except 2 helicities. Right? And then going back to our convention, this is the one with 2 minuses and the rest pluses. Okay? And then there's a terminology that I can consider next to blah, and put an n. So if I have n MHV next to maximally helicity violating, means I have 3 minuses and the rest pluses, right? And then I can put an n, have 4, and so on. This, of course, is only useful if I'm talking about very large n, right? Because for the 4 points, MHV already is 2 pluses, 2 minuses, right? Anyway, so why define this and this hierarchy, MHV, NMHV, NMHV, and so on? Well, obviously because MHV is the simplest, and then it gets more complicated once you start putting n's. So turns out then that for MHV amplitudes, we can write a formula known as the Park-Taylor formula. Which is for the MHD amplitude. And then I say that the I and J are the ones with flipped indices. And that is the somewhat obvious generalization of this. If I see that I can rewrite this like this, right? I just multiply up and down with 1, 2. Then I know that this is a cyclic product, 1, 2, 2, 3, 3, 1. So the general formula then is I j to the fourth over 1, 2, 2, 3, and 1. Okay? So this formula was stated. There was some sort of proof, but not truly complete. The true proof of this came with the BCFW construction. And in order to prove the BCFW construction, we will need this complex 3-point amplitude. So that's why we started with this. But before we get to that, I would like to make some observations about the possible independent color-ordered amplitudes. So it seemed to us that the color-ordered amplitudes were all independent. So 1 to n. So this is one possibility, but then I could in principle have considered, let's say, 2, 1, 3, n, and so on. All sorts of amplitudes where I permute the various particles inside the amplitude. And because you remember the full color amplitude n is the sum of traces and then the permutations of these. So in principle, you might think that all of these terms that are in this sum are independent. But the aim is to show that they're not all independent. There are relations between the various terms in the sum, meaning the terms where I permute the particles inside the color-ordered amplitude. And these are called Kleist-Kloif relations and BCJ relations. This is Bern, Carrasco, and Johansson. All right. So, well, before these relations, there's one more relation that is important, is a reflection invariance. So, we know that trace for matrix is equal to its dagger. So that means that trace PA1, PAN is equal to trace of its dagger, and in the dagger I have the opposite order, right? When I take the dagger. But then these things are self-adjoint anyway, so I can remove the dagger. So I have the trace with an order is equal to the trace with the opposite order. But this multiplies an amplitude, color order amplitude. So that means, oh, sorry. No, sorry. Yeah, it's not self-adjoint. It's with a minus, but then that means I get a minus to the n. Getting confused. But that means that a n of 1 to n is equal to minus 1 to the n, a n of n to 1. Right? Okay, so one relation between these things. But then this Kleist or KK relation are written like this. So these are some orderings. Okay? So there's a set of indices that are written in some order. Then in here, OP stands for ordered permutation. So this means that I have a permutation of all these objects, the alphas and the betas, but inside this ordering, I keep the order of alphas in the original one and the order of beta transposed in the original one. Okay? And then yeah, and beta is the number of labels. Number of labels in the set beta. So if I have 3 objects in here, then it's minus 1 to the 3, and so on. All right. So reflection, KK. I also have the U1 decoupling relation. So to prove this, I can consider one of the TAs to be proportional to the identity. So I have a trace in the full amplitude. I have a trace of TA sigma of 1, TA sigma of n, then AN sigma of 1, sigma of n. And then take one of these things to be proportional to the identity. And then you get the sum of the permutations. And after some algebra, what you find is that there's a sum of amplitudes that is equal to 0. So So specifically, what happens is I can permute. So if this is an nth position, let's say I keep n fixed, and then permute cyclically the other ones. Well, sorry, not cyclically. Permute all the other ones. Yeah, so A1 to n. Let's see, 1, 2, 3, 4 plus an 2, 1, 3, 4 n plus an 2, 3, 4, 1 n equal to 0. Okay. Okay, so now let's try to understand how many independent objects we have. So initially, I start with having n factorial possible permutations, right? But then I know that cyclicity, this is color ordered, and then cyclicity is irrelevant in here. So that must give us a division by an n, right? N amplitudes, the cyclic amplitude of a given amplitude, they're identical. So I divide by n, I'm left with n minus 1 factorial. So from cyclicity. But then the Cauchy relations, well, as you can see, you fix 2 points, and then rewrite the remaining permutations in terms of these ones. So these amounts to so this reduction amounted to fixing 1 point, let's say 1. 1 is always on the first position. And then the other ones in here are permuted. And then this Cauchy relation amounts to fixing also the second one. Because when it's not fixed, I can rewrite in terms of the equations where it is fixed. Right? So that means that instead of n minus 1 factorial, now I have n minus 2 factorial for all possible permutations of the objects in the middle, which are n minus 2 objects. Okay, so we say that cyclicity plus kk means there are n minus 2 factorial independent amplitudes. And I can choose the kk basis, which amounts to, as I said, fixing 1 and n. Right? But that's not the end of it. I can reduce further. So there's one more relation, one more set of relations. These are the Bern, Carrasco, and Johansson relations. And these are a little bit more convoluted to understand. So we have, we have to think about how the three amplitudes are written. So there's a three amplitude like this, and then that means every line in the three amplitude is some sum of the external momentum. So on every line, some sum of external momentum. So let's call them K1 until KL. And then that means that the denominator for that, so that's a propagator, it's 1 over p squared. But p is equal to this. So this is what I would call either QL squared or SL if you want. So then it means that really AM, the amplitude, so this would be for a Feynman diagram, right? But then the amplitude is the sum of Feynman diagrams. So it's sum of a term, is a sum of terms like this, where there's some numerator, and then there's a product of these SLs. Okay. It's a cryptic notation, but you understand. So there's, for each Feynman diagram, there's a product of propagators, and each propagator contains such an object. So there's a product of these propagators, but then this AK just means whatever SLs mean in here. And there's a sum of these terms. It's not very precise, but it just describes really how this is supposed to look like. And then, so this is the color order amplitude. Okay? And from it, we write the full amplitude by multiplying with the traces of generators. But remember that that I said the traces of the generators could be rewritten in terms of Fs, right? Reversely. So there was a relation between either Fs or traces of generators. So I had the relation that F tilde ABC was trace TA TB TC minus trace TA TC TB, right? And then that means that the full amplitude is written as by taking this and adding, so these numerators, adding some color factor Ci. These are products of F tilde ABC. One can associate them with some Feynman diagrams. So Feynman diagrams for FABC if you want. And then the same thing. Okay? Okay, so the color order amplitude is of this type, then the full amplitude is just multiplied by some color factors which come from F tilde's ABC. The non-trivial thing is that the CIs satisfy Jacobi-like identities of this type. But then BCJ showed that the numerators in K can be manipulated to also satisfy this. So that amounts then to a color kinematic duality. color for Ci, kinematic for Ni. Okay. So we find the relation for Ci's, the Jacobi relation for Ci's, and from them we deduce a relation between Ni's, Ni plus Nj plus Nk equals 0. But the numerators, they are, the relation between numerators amount to a relation between amplitudes, right? So so first let's say first we solve Ni plus Nj plus Nk equals 0 relations. Remember, this is schematic and it amounts to, for every amplitude there is such a relation, so that allows us in fact to solve for n minus 2 factorial independent Ni's. And then, so I'm being very schematic because the details are a little bit complicated, but I'll give one example to make it more concrete. Then you can put these numerators in a vector n, meaning n1, n2, and so on. Right? Then, and the amplitudes also in a vector A. Again, I'm being schematic. Now A1 stands for one of these terms with a given ordering. So then, these relations between amplitudes and numerators amount to saying that there is a matrix relation between vectors, right? So I have a bunch of n's and a bunch of a's, and the relation between them is linear, and so I can write a matrix between them. But then, the fact that there is a relation Ni plus Nj plus Nk between the n's, that means that all of these vectors are not linearly independent. Means that m has, in fact, less than the total, which would be total would be n minus 2 factorial. Less than this, and it has, in fact, n minus 3 factorial vectors with 0 eigenvalues. With 0 eigenvalue. Meaning that they are linearly independent eigenvectors. They are linearly dependent eigenvectors, right? For each 0 eigenvalue, there is a linearly dependent eigenvector. So that means that in fact, we can have n minus 3 factorial linearly independent amplitudes or numerators. Okay? All right, I realize this is all a lot to take in, so it's important to take one example at least, the simplest one, the 4-point function, the 4-point amplitude. and see how that works. So the Mandelstam variables are STU in this case. So this is 4 factorial amplitudes would be 4 indices, 4 particles. But then I said by simplicity I reduce this to 3 factorial. That's 6, right? But then by reflection invariance, I'm left with 3. But then by KK relations, in principle I could use already the KK relations. There are several of them, but they are dependent, as we'll see. So if you consider reflection invariance, there's only one independent KK relation, so we're left with 2. And then using BCJ, we're left with 1. So let's see that all of the KK relations in fact reduce to 1. So the 6 amplitudes for which I would write them would be A4, 1, 2, 3, 4, then 1, 2, 4, 3, 1, 3, 2, 4, 1, 3, 4, 2, 1, 4, 2, 3, 1, 4, 3, 2, right? This would be the 6 amplitudes. And then the KK relations would amount to rewriting these things in terms of something else. So remember, I erased it, but this was 1 alpha and beta, right? So beta is null for this one, right? Because 4 is n equal 4 in our case. 4 is already on the last position. So this is kind of trivial. This is just nothing. Then I can also have this one where it's also on the last position. This is also trivial. Okay. Now this one. So you see the set alpha is 2, the set beta is 3. And this is it written in terms of permutations, where I keep 1 and n, that is 4, the first and last position. And then in here I permute, but keeping the order inside alpha and the order inside beta fixed. Well, the order inside alpha and beta are just one label each, so there's no constraint on the permutations. So the only possibility then is, there was a minus here, is to sum 2, 3, and the other one, A, 4, 1, 4, 3, 2. Okay? This was the only thing. Now let's do this one, where I also have one alpha and beta are both of one index. And then I get similarly minus A4, 1, 4, 2, 3, plus 4, 4, 3, 2. So this is the same as A4, 1, 2, 4, 3, right? It's the same. Right. And but so it would seem like this one gives us a non-trivial relation, but this is not non-trivial because if I use reflection invariance, this is equal to A4 2 4 3 1. And now I use cyclicity, I put this in the first position, and I get 1 2 4 3. Okay? So using cyclicity and reflection invariant, these two KK relations reduce to only 1. And in here, the last ones are also trivial because sorry. Actually, so I would have to put it on the last position, and then this would be alpha, and I here with some permutations of alpha. So no, sorry, this would be beta, yes. And there are some of the permutations of oh no, yeah, I some of the permutation of beta, but where beta transpose is fixed, so nothing. This is 1 of 4. 2 3. This is 1 4 3 2. And let's see, 4 3 2 1 1 4. Yeah. Oh no, yeah. I have to transpose them though. Yeah, that's the point. But then this is again trivial by reflection invariance and cyclicity. Reflection invariance means this is A4 4 2 3 1. And then by cyclicity, I put the 1 in the first position and I get back this. And similarly here, reflection invariance gives me 4, 3, 2, 1. And cyclicity, I put this on first, so I get back to this. So you see, by using cyclicity and reflection invariance, the KK relations reduce to a single one that then use this. And finally, let's see the BCJ relation. Oh, yeah. So then I should have erased here. Erase just the upper half. All right. So, what are the color factors in this case? Well, for the 4-point amplitude, the color factors would be defined this way: F tilde A1, AI, AJ, B, F tilde B, AK, AL. Okay? So you could see that this is the case because 3 amplitudes are of this type, right? 3 amplitudes in the 4-point case are of this type. And this is a gauge 3-point vertex, which will come with an F tilde ABC, and this with an F tilde ABC. But there's one thing that would be summed over. There's this index that's summed over, so really I have things like this: AI, AJ, B. Here I have B, AK, AL. Okay? So this is the color factor that appears in the 4-point amplitude. And then I can, so these are identified by I, J, K, and L. But as you know, the 4.3 amplitudes, they're in fact characterized as S channel, T channel, and U channel. So I can denote them as CU, correspondingly to the S channel, T channel, and U channel amplitudes. This would be F tilde A2, A4, B, F tilde B, A3, A1, C, S, F tilde A1, A2, B, F tilde B, A3, A4, and CT, F tilde A2, A3, B, F tilde B, A4, A1. All right? And then you can do algebra to show that these satisfy this relation. And then just flip the sign of CS, redefine C tilde S is C minus CS, and then this amounts to CS plus CT plus CU equals 0, okay, which was the Jacobi type identity that I described in here. And then, correspondingly, you can find linear combinations of numerators that satisfy the same relation. You can find NS numerators that satisfy NS equal NT plus NU, or correspondingly, the sum is equal to 0. And to see how this goes, so I'll not show you what the numerators are, but you get that A4, 1, 2, 3, 4, which was equal to A4, 1, 4, 2, 3, is NS over S plus NT over T. Okay, so remember, it's a numerator times a propagator. So the propagator has a pole, which is 1 over S in this case, and in this case it's 1 over T. And then A4, 1, 3, 2, 4, which was A4, 1, 4, 2, 3, according to the K relations. This is minus NT over T plus NU over U. And A4, 1, 2, 4, 3, which is A4, 1, 3, 4, 2, is minus NS over S minus NU over U. So from this you can check, this one you can explicitly check this last independent KK relation that A4 1, 2, 3, 4 plus A4 1, 3, 2, 4 plus A4 1, 2, 4, 3 equal to 0. But you could also find a BCJ relation, which is in this case S14 1, 2, 3, 4 minus S13 A4 1, 2, 4, 3 is equal to 0. And this S14 is by definition equal to T. S14 means K1 plus K4 squared, but this is T. And S13 means K1 plus K3 squared, but this is U. So the relation that is immediately checked from this is that T times A4 1, 2, 3, 4, so T times this minus U times this is equal to 0. Okay? So you can check this, but you see this is now a relation between amplitudes, saying that the only independent amplitude is 1, 2, 3, 4. All right. Okay, so the conclusion of all of this is that, you can reduce, even though it seems like you have a bunch of possible amplitudes depending on the particle momenta and helicity, that you actually have much less. Right? So in the case of the 4-point amplitude, you have actually just one. There's only one that's relevant. There's not many. So finally, let's go to the BCFW construction. That's Brito, Kashazov, Feng, and Witten. And they use the fact of analyticity in momenta. So analyticity in general means that you can reconstruct a function from its singular points. It's not actually analyticity, specifically meromorphicity, which means a function that is analytic everywhere except for poles, for single poles. Now, why didn't people do this before? Why it took these 4 smart people to figure this out? Well, because in general, an amplitude is a function of an n-point amplitude is a function of n momenta. And so the natural thing that people thought of before was, well, you have a function that is supposed to be analytic, or look at analyticity properties as a function of n complex momenta. And multi-complex variable analysis is extremely difficult. That's the point. So the analysis of extracting stuff from this analyticity condition would be extremely complicated. But BCFW thought of a trick. Then, if it's complicated, let's reduce it as at dependence of one complex variable. So consider one complex deformation of momentum. By a complex number z. And then using this, they were able to show that you can find an from an minus 1. All right. So how do you do this? Well, the other thing is you have complex momenta, but there's one thing that you should preserve, which is the momentum conservation. So the trick was to use this helicity spinor formalism. And so you have lambdas and lambda tildes instead of p's. And so the deformation is you take one of the lambdas and you deform it to a lambda hat, which is lambda plus z lambda n. N is the other one, is one of the other ones. And then lambda n itself is unchanged. But on the other hand, lambda tilde 1 is unchanged, but lambda n is changed to, but lambda tilde n is changed to lambda tilde hat, which is lambda tilde n minus z lambda tilde 1. Okay? And then since the momenta are lambda times lambda tilde, so then k1 hat of z AB dot, is lambda 1a, lambda 1 tilde b dot. But then the deformation, in lambda 1, the deformation is only lambda, so it's z lambda n a lambda 1 tilde b dot, right? The deformation is just in the first term, so the second is the same, the factor. whereas for n, I have the same thing, just that now with a minus. So the deformation is now. So in lambdas, the deformation was with plus and plus lambda n. And here I have with minus and with minus lambda 1, minus lambda tilde 1. So you see it amounts to the same thing, which means that for the sum, nothing changes. So k1 z plus kn z ab dot is equal to k1 z plus kn, is equal to k1 plus kn ab dot. Right? The z deformation does not change the momentum conservation. And since we still have factorization in lambda lambda tilde, that also, so we deform just individual lambda lambda tilde, not the momentum. That means that we still have k1 hat squared of z is on shell, so is 0. Okay? The factorization of momentum into lambda lambda tilde was equivalent to it being on shell massless, k squared equals 0. Okay. So, with these properties, now we are able to say something about analyticity. All right, so the amplitudes, the three amplitudes, will have denominators of the type qn squared. As we saw, the momentums on propagators. But then it means that this thing is a rational function. And this thing will contain, in general, the complex number z. So Q was sum of momenta, of external momenta, right? And those depend on z. I mean, 1 and n only, but in principle they could depend. However, there's only one such thing. So that means that we have a numerator that can depend on z, but linearly only. Sorry, not linearly, yeah, just. And then in here we'll have products of these QLs. And so this would be things like z minus stuff, product z minus z1, z minus zn, and here z minus some other z tilde 1, z minus z tilde n, right? So, all in all, the amplitude will be a rational function of z. Rational means just products of z minus z i's. And such a function, obviously, by definition, is meromorphic, which, as I said, means analytic except poles. Moreover, there's a step that takes some time to do, and but I avoid it. That one can usually prove that an of z, this an hat of z, this function of z, goes to 0 as z goes to infinity. Okay, so it's a deformation in momentum, and usually you can show that when you go with complex momentum to infinity, the amplitude goes to 0. So that's kind of natural, right? You don't want your amplitude to blow up. That means that there's no pole at infinity, which means that the integral at around infinity gives 0. So, so it means we can use the Cauchy theorem to relate relate the function at z equal to 0, which is by definition an, to the residue at its other poles. So, to be more precise then, okay, this is the fact that there's no residue at infinity. This is the statement that there's no residue at infinity. But then this gives a function at z equals 0 plus sum of the residues at zk. So that means that an, which is an at z equal to 0, is minus the sum of residues of the z. All right. Let me see. Now, the pole in the propagator at each residues, so pole in the denominator for each residue is for zpi squared zk. This pi of z is the momentum on the propagator. So, remembering that the poles of the amplitude, they're all coming from the propagators in some Feynman diagram, right? So the Feynman diagram has these propagators, and when they become on shell, that gives a pole in the amplitude, right? So all the poles in the amplitude are of this type, and then this pi of z is the momentum on this propagator. And then when the momentum, so the pole corresponds to this pi squared equal to 0, right? But then this is always, the momentum on the propagator is always the sum of the external momenta. So sum of external momenta. And then, in order for it to be a pole in the amplitude an of z, that means it has to depend on z. But the z dependence only comes from K1 and Kn. So that means that one of them is K1 or Kn. Okay? So let's choose it to be K1. I mean, it's the same for Kn, but let's choose it this way. Then Pi of Z will be K1 hat of Z plus some other things. Other momentum. Kr. Some Kr. Then Pi squared of Z, K, Pi squared of ZK, this thing, would be Ki of Zk, K1 of Zk plus, here the other thing will be called just Pi, the part that is Z independent. And then this thing, K1, is this thing, right? So the deformation, it's not Pi prime rather. So this one, so the full sum then would be Pi, wherein Pi I included Pi prime and K1, giving this term. And then plus Z lambda n lambda 1 tilde. Okay, and Z is Zk in this case. So this is equal to Pi squared plus 2Zk 2Zk Pi dot lambda n lambda 1 tilde. Where I use that the fact that this thing squared is equal to 0. A lambda times lambda tilde is equal to 0. That's the point about the helicity spinor formalism. Okay, so so putting this to 0 at the pole, by definition Zk is where this is equal to 0, means that Zk is equal to minus Pi squared over 2Pi dot lambda n lambda 1 tilde. But the residue in here, so the residue in here has also a Z, right? So I'm looking at the amplitude divided by Z. So what I have is Z Pi hat squared. Zk is approximately equal to, well, Z is approximately equal to Zk, but then this thing becomes, well, this is 0 at the pole, that's the definition, and then the small deviation is 2Z minus Zk times Pi times lambda minus lambda 2, right? 2Z minus Zk Pi dot lambda n lambda 1 2. But then substituting this in here, you see I get Pi lambda n lambda tilde is equal to minus Pi squared over Zk. Zk also cancelled, so this is equal to minus 2 Pi squared Z minus Zk. No, 2 cancels as well. Z minus Zk. Alright? So at the pole, near the pole, this thing that blows out, whose residue we're calculating, takes this value. Alright, so now finally, I have that this relationship that a n into n is equal. Well, so I've just calculated that there's a pole that's approximately equal to this. So let's divide by it. Oh, yes. When I calculate the residue, I mean that this is being cancelled, right? Residue means I write the function. So I write the function as the residue divided by z minus zk, right? So when I calculate the residue, I just erase z minus zk. Then downstairs I'm left with just minus pi squared. But there was one more minus in here, so I'm left with 1 over pi squared. Okay? And then what? Then I remember what this amplitude was. So the point, the point about the pole in this amplitude was this was getting on shell, right? This propagator was getting on shell, in which case I have a certain endpoint, well, a certain k point amplitude to the left and an n minus k point amplitude to the right. Okay? Because in the Feynman diagram, in the corresponding Feynman diagram that was blowing up, right? To the left, I have, this looks like a tree diagram, and moreover, this line is now also on shell. And here the same thing. Everything is on shell, and this is also on shell, and it's still a tree amplitude. Okay? So let's say near the pole, AN splits into A left and A right to 3 amplitudes, connected by the propagator. And then for the propagator, we've calculated what happens, so we took care of it. So let's call this, I'll call this AR plus 1, and here AN minus R plus 1. Because, let's say these are external lines, and here I have n minus r external lines, right? Then this amplitude to the left of the cut has these r external lines plus 1 from the propagator that was cut. And this one similarly has n minus r plus the 1 from the propagator that was cut. Okay. Then in here I will have 1, 2 until r. And here I will have r plus 1 till n minus 1 m. And then in here I will put this propagator that is cut, so pi and here minus pi. And remember, what we're interested in is amplitudes of given momenta and helicity. So these things have given momenta and helicity, and then it means I also have to sum over helicities. So the momentum is fixed because I make it blow up, but the helicity now has to be summed over. So let me put here plus h and here minus h meaning helicity, and sum over it, sum over h being plus or minus. And then I also have to remember that this is a sum of the residues, so I have to sum of all these r's, where all these propagators blow up. Okay? So from 2 to n minus 2. Yeah, and the only constraint is that we don't have a 2-point amplitude, we only have a 3-point amplitude. So these things can go, we need to have at least a 3-point amplitude to the left and at least to the right. So that's why I sum from 2 r equal to 2 to n minus 2. Okay. All right. So finally, the last thing to do is to show that this, so this is the BCFW construction. Right, so it's a way, then, as you can see, it's a way to calculate n-point amplitudes, knowing all lower point amplitudes until n minus 1, right? Now, in principle, this, I haven't said what the helicities are, so this is valid for all helicities. So this is a general construction. But the simplest application of the BCFW is in the case of MHV amplitudes, maximally helicity violating, in which we can take this formula and use it to prove the Park-Taylor formula inductively. So, proof of Park-Taylor, inductive proof of Park-Taylor using BCFW. All right. So this is for AN MHV, and 3, of course, where I put 1 plus, 2 plus, and then, as we said, I minus, J minus, all the rest plus. Oh, sorry. Yeah, I can arrange, by cyclicity, I can arrange that's useful to put the minus on the last one. Okay. So in this sum, I have sum of R from 3 to n minus 3, in fact, because we remember there's one more constraint that we're using. So, you know, we've used complex momenta to find the BCFW construction. But in the end, the BCFW construction itself relates amplitudes with real momenta. And for real momenta, we saw that the 3-point amplitude actually vanishes. So the first one that's non-trivial is the 4-point amplitude. Right? So first AN B from 0 is A4. So that means, in actual fact, to use it for to use it for MHV amplitudes, I need to consider the sum from at least a 4-point amplitude to the left and a 4-point amplitude to the right, which means summing from 3 down to n minus 3, right? No, sorry, I'm wait a minute, I'm getting confused. No. No. Sorry. No, I'm completely wrong. Yes. So yeah, the formula is not for real amplitudes. Yes, it's 1 and n are still complex, and also moreover I is complex. I mean, it's at the pole, but the pole is complex. It's not the real pole. So it's actually the exact opposite. So if I consider this sum, with at least a 4-point amplitude on each side, then the amplitude I consider yeah. So one of these things is a minus. The rest are pluses. Then in here I have sum of plus and minus, but on one side is minus h, on the other side is plus h. So I can have plus minus or minus plus in here, right? So n is a minus, and then I is a minus. So yeah. So let's say I is on this side. If I is on this side, then you see in this first combination I have 2 minuses on the right, but 1 minus on the left. And the thing with only 1 minus is 0. Or I can have 2 minus on the left and plus on the right, in which case I have 2 minus on the left, that's non-zero. But here I have only 1 minus, so that's 0. And then if I put minus I equal minus on the right, I have 2 minuses here, so that's always non-zero. But in here I have only pluses and at most a minus from the helicity h. So this will always be 0. So you see all possibilities give 0. So I'm left with r equal to 2 and n minus 2. And if I have n minus 2, r equal to n minus 2, then what can we have? Well, r minus 2 means I have a n minus 1 and here a three. So a n minus 1 on the side and a3 on the other. And then this one will have minus for n, plus for n minus 1. And then in here I can have h, and in here minus h. But So if I is in here, then I can have minus. And the only possibility for this to be non-zero would be for h to be minus, in which case here would be plus. And now this one, this one is proportional to, this one was proportional to, so if this lambda tildes are non-zero, I mean, yeah, if lambda tilde are non-zero, then this is non-zero, but the shift was blah blah. The shift was lambda tilde n minus z lambda tilde 1. So why is this non-zero then? Oh, yeah. Yes, I'm sorry. Yeah. They are actually proportional. So the point is, this is pi. So this is depending on z. So this has this lambda tilde n in it. So that means that lambda tildes are actually proportional. So lambda tildes are proportional, so that means this is 0. Because this is only non-zero if lambda tildes are not proportional. And then if I is greater than n minus 1, then already here I have a3 minus plus minus. And well, now similar argument will give that this should be proportional to lambdas to be different from 0, but in fact this thing depends now on lambda, and the lambdas are actually proportional. So this is also 0. All right, so we've shown that all the terms except r equal to 2 were 0. So r equal to 2 remains. And then I have a3 of 1, 2 with well, okay, let me write it here. Okay. So I get a3 an of 1 plus 2 plus n minus 1 plus n minus is a3 of 1 plus 2 plus, and then in order for this to be minus, we have minus. In order for this to be non-zero, I need the third to have minus in this t. And then I over p squared an minus 1 of p hat now has opposite helicity plus 3 plus n minus 1 minus plus n minus. All right. And this thing here is minus I times 1, 2 cubed divided by 2 bracket with minus p hat. And then minus p hat bracket with 1. Sorry, like this. And then well, the minus in here kills the minus in here, so this is plus I 1, 2 cubed. And then 2 p 1 hat. But then 1, 2. Oh yeah, this is this should have been 1, 1, 2. But then this means lambda 1 hat dot lambda 2. Sorry, tilde, right? But the deformation is in lambda. So this is equal to the same 2, which is the same 1, 2. So I can remove the hat. Yeah, the same thing here. On the other hand, on the thing that we want to prove, the Park-Taylor identity of a n minus 1 with some p plus 3 plus I minus n minus 1 plus n minus. So the assumption is the n minus 1 step, which applied to the amplitude with this particular set of helicities amounts to, well, sorry. Yeah, IN are the ones with minuses, so this is IN product to the fourth, and then here the cyclic ones, so P hat 3, then 3, 4, n minus 1 n, and n p hat. All right. So assuming this, now we have shown that an is equal to this one times this times n minus 1. So implies an is equal to this thing times 1, 2 cubed divided by 2p p1 and then times I over p squared. Oh yeah, and the point was, of course, that the amplitude in here is for 1, 2 going to p, but then p squared by momentum conservation is equal to k1 plus k2 squared. So that's S12, and S12 by our spinor relation is equal to this product. So I can remove this p squared and say this is 1, 2, 2, 1. All right. Yeah, all right. So the last step is actually, I left it as an exercise, but I mean it's a little bit of algebra. I mean, the first thing you see is you cancel this with one of these things and get a minus, but then you have to substitute in here what p hat actually is and calculate these products and see that you revert to the formula that you want to prove, which is of this type. So only with square brackets, only with angle brackets. All right, so there's a little bit of algebra involved, but it can be done. All right. So, in conclusion, we have seen that we can use the BCFW construction to prove this Park-Taylor formula for MFB and MHV amplitudes. But moreover, we could also use it for any kind of amplitude. It's just that in the case of other amplitudes, we don't have a compact formula for any endpoint function. But otherwise, you can just use it recursively to calculate the endpoint amplitude by knowing the lower point amplitudes. So this takes a little bit of work, of course, but in some cases it's simpler than doing it in any other way. All right, so that's everything I wanted to tell you today. Do you have any more questions about this? All right, so in any case, this is, as I said, this lecture was not intended for the exam. This is just for your benefit, since this is a very active area of research nowadays. Yeah, do you have any other questions from previous lectures as well? Well then, that's it then, and I'll see you on Wednesday for the final exam. Oh, and please give me the last exercises and pick up exercises from here.
This is late, you haven't finished the last one.
Okay.